Thanks for the introduction. So it is our second meeting. In initial lecture, we saw that how remote sensing is changing the agriculture. So basically, now we are once in the earlier lecture we saw that how remote sensing is changing agriculture, as well as some of the applications were shown by Bimal sir. So now we are at this stage where where we have satellite data, and we want to process it. That part is missing. You have the data, you have the some problem statement related to any domain, and you want to solve it. You know the techniques, you have the data, but the data as seen by the satellite cannot be directly given to the machine learning algorithms. So it requires some understanding of the data and some pre-processing steps, so which I'm going to discuss in this session. So the objective of the session is that at the end of the lecture, you will be able to do manipulation of geospatial data using Python and other GIS libraries. And you will also able to perform pre-processing of satellite images based on your AI/ML application, which you want to target. So the agenda is that this whole session is divided into three parts, where in the first part, we will see the basics of GIS and related terminologies which are commonly used to define or to characterize satellite data. And the second is some of the common geospatial Python libraries that you can use in your project. And the third one is that we will see in the third part that how we can use these libraries to do some of the GIS operations such as mosaicing, reprojection, georeferencing, some band operation using NumPy, clipping. Maybe you are listening these words the first time. It may be very hard to understand right now, but after this lecture, you will be able to understand all these kind of GIS functionalities. So first, we start with the common GIS terminologies. In your school days, you must have been gone through all these latitude, longitude, what exactly these are. So just to refreshing these concept, that latitude is basically an angular distance from the equator, whereas longitude is angular distance from the prime meridian. Okay, why we use latitude and longitude? Can anybody tell? Very common questions. Mark any location. Okay. There is one important thing is that you are 50% correct. Mark uniquely. We want that these locations which are uniquely determined by the coordinates, so everybody can understand where on the earth this particular point is. This is the main objective of latitude longitude. In basically in GIS there are three terms. One is the location, which is defined by the coordinates. Another thing is distance. Okay, so what are the basic properties of distance function? You are learning AI/ML, so I think somebody can tell me. Should be. Okay, it should not change. Okay, any other? There are three prime properties. It should not be negative, right? And another is triangular inequalities. Okay, I think so. Basically, because these three things, I mean, the measures in the distance can be measured in GIS using three parameters. One is the linear distance, which is measured in terms of meter, that is the length between 2 points A and B. Another is the angular distance, which are, so an example are latitude and longitude. The third one is great circle distance or the Haversine distance, which is typically used in such a case where 2 points are geographically very distant. So this is a basic thing. Now coming to the another point, that another GIS terminology, which is image projection. What is image projection? So basically projection is nothing but a mathematical model which is used to project 3D surface of the earth on 2D map. Because whatever we are having right now, in fact the computer screen that you are watching is a 2D plane. So but the surface of the earth is a 3D. So how you want to mathematically model that particular 3D surface of the earth on your computer is basically nothing but the projection is. So typically there are three types of projection. based on the on which surface we are actually getting the projection. So here there are two concepts. One is the projection, on which surface we are taking the projection of the latitude and longitude, and another one is a perspective, which is nothing but the light source, where the light source is, and based on the light source we are getting the image of that particular location on a particular surface, which is called projection, which we call projection surface. So basically here in this example, as shown here, the light source is at the center of the earth, and this is the globe, and we are capturing the, let's say if there is a, at this point there is a, there is an object, and we are capturing its projection on this cylindrical surface. So this projection is called cylindrical projection, and uh, if this cylinder is close to, very close to our surface, so obviously the errors at the surface will be lower, because if you move from the equator to the polar side, as the latitude increases, the error or the distance between two latitudes is increasing. So that is why this projection are basically, every projection has some limitation, and there are four property associated with the projection. One is area, another thing is distance, then direction and the shape. But you cannot, there is no such projection which preserve all these four properties. So here in this case, the distance between latitude is increasing when you are going from equator to the polar side. Similarly, another projection surface can be a cone. So such type of projections are called conical projections, and which are typically useful for the mid latitude. So in case of conical projection, the two side of the cone passes very closely to the Earth's surface, and where the error is minimal. And it typically happens so that it is very close to the mid latitude, and that is why it is suitable for mid latitude areas. Another example is planar projection, which is suitable for pole side map display, where you see that if here is a source of light, then you take the projection on the pole, on a where you assume that the projection surface is a simple plane, and you are taking the projection directly, since the poles are very close to the surface and the errors are minimal. So based on that, you identify that at which location you are working on and which projection you want to use for your applications. Now coming to the coordinate system. So basically it is a system used to identify a point uniquely on the surface of the earth, as we discussed earlier. So basically there are two types of coordinate system. One is unprojected coordinate system, which means we have given the lat long and a particular value at that location explicitly to the system. And another way is projected coordinate system, where the which tells us that where the point is located on the 2D map on the surface. So basically it considers the mathematical functionality in itself. That's why we call it a projected coordinate system. Now another term is datum, which is basically the objective of all these projection system is to model Earth. And so the scientist and the mathematician have trying to generate a closed mathematical model which can idealize the Earth's surface as close as possible. But it is not possible because of the Earth's surface, diluting Earth's surface, where somewhere there is a very large mountain, somewhere there is a very deep point in the ocean. So it is very hard to map Earth's surface. So they have come up with a simplified model which can be generated from the mathematics, which is called datum. So there are two types of datum. One is local datum. So local datum is typically used in the areas where we are getting minimal error. For example, in North American datum, which is next is 27, which means it is defined in 1927. In case of the North America, the surface of the Earth, which is modeled, passes very close to the actual Earth surface, which means there is no error or the minimum error at all. But if the same datum I am using for the European countries, for example, this here is Europe, but if I am using the same datum for mapping or for the projecting European countries, so it is very hard. I will get a lot of error while doing the projection. So therefore, there are two concepts. One is local datum and another is global datum. And what happens that in case of geostationary satellite, where we want to capture Earth in a single shot, we cannot use local datum because half of the earth at least we are capturing from, we are seeing from the satellite side. So therefore we need to define global datum also. And there is one standard WGS 84 which is for world geodetic system 1984. So here some of the mathematical values, for example, what is the diameter of the earth? Since earth is in bulge shape, it is so the radius at the equator is more as compared to the pole side. So it has some bulgy shape. So there is some difference in the diameter which is given over here. So these kind of parameters are given to the to generate mathematical model, and it is one example of global datum. So this is how a projection looks like. A standard projection looks like in well-known text in WKT format. Now the first basic thing is covered. So now you know what is the projection, which projection is useful at what location. Some of the mathematical things like datum, you understand all these things, you understand what is coordinate reference system. Now we are moving toward the data, how we interpret data for the geoprocessing. So basically there are two types of data. One is raster data and this vector data. Raster data is typically used to show a continuous data. For example, if I have to see, if I have one image in front of myself where I am getting the temperature profile of Earth. So it is a global temperature I want to see. So in that case, for every pixel on Earth, I am getting one temperature value. To show these kind of continuous data in a spatial domain, we use raster data. Similarly, there is another data called vector data, which are nothing but basic geometries that you see in mathematics. For example, if you want to, so these geometries are point, line, and polygon. So one example is here, where you can see that what is the difference between these kind of data. So let's say if you want to uniquely determine the hotels in a particular city, let's say in Ahmedabad. So in that case, let's say there are 100 hotels in Ahmedabad and you want to uniquely identify these hotels. So automatically you will say, okay, I have latitude, longitude, or maybe one attribute associated with that particular latitude, let's say hotel name. So only these three data information is available with us. So you will not use raster dataset for that, because in case if you use the raster dataset, only pixels, only those pixels where these coordinates are will be marked as the hotel, and remaining other pixels will be filled with no data values. No data value means a system, a GIS system understand that these are the valid pixel, but it do not take care, do not see them as a valid pixel values. So in that case, lots of memory, lots of space will not be utilized. So in that case, we will prefer to use vector data set. So wherever your data is sparse, you use vector data set. But similarly, another example is line. So this is the ski line. So where the ski line passes through on the earth. So if you use raster data set, in that case, this is not the correct way, because the pixels have to be in the straight line, in either in vertical direction or in the horizontal direction, which is not the case in case of the vector data when you define it based on the line. Similarly, for areas, road network, this is the only case where we want to use the raster data. So so the data is in continuous space in a spatial domain, and we want to see that at every pixel what is the DEM value. For example, in this case, in that case, raster data set, raster representation of data will be more accurate rather than the vector data. Now the term is geotransform. So basically, geotransform is an affine transformation from image coordinate system to georeference coordinate system. And why it is used? Because once you capture an image from the satellite, it won't tell you that which pixel belongs to at what place. You have to explicitly define the system, explicitly tell the system based on geoprojection that what coordinate is linked to a particular pixel. So basically, geotransform is defined by 6 parameters, which are the upper left coordinates, which are given as x0 and y0 in this picture. Then the pixel size, pixel resolution in x direction and pixel resolution in y direction. Typically what happens in mathematics, you see this as a 0, 0, right? In mathematics, you start with the lower left 0, 0, then it is 0 row, 1 column like this. But in case of GIS or image system, which is used here, we start with this coordinate. Okay, so one value is the upper left coordinates x0 and y0. Another one is the pixel resolution in x direction and the y direction. And sometimes it so happens that your satellite is moving in particular direction. So you want to introduce that shear effect also in this image. So you have to mention the row rotation as well as column rotation. But nowadays, most of the data that you are having in open domain are already north aligned. So in that case, it's typically 0. So all these 6 parameters are important to associate spatial information with the image. So just for a revision, we have one image with us and we want to tell the system, okay, which pixel belongs to which location. We need two things. One is the geo transformation, another is the projection system. So these two things are important to understand. That is the crux of this whole 15 to 20 minutes. Now, why we want to use raster IO or NumPy, I mean, these kind of libraries instead of standard GIS software. So just to tell you that there are some software, for example, ArcGIS, QGIS, which are typically designed for the understanding of the satellite data and to do the geospatial manipulation of the data. But why do we don't want to use it? Because as a researcher or as a AI/ML practitioner, you want to develop your own custom algorithms or processes. So in that case, it is so possible. It may be possible that the particular functionality is not available in that GIS software. In that case, it will help you out because Python has lots of functionalities, lots of libraries, and you can in fact develop your own algorithm on this. So that is why it is very important. Another thing is that AI/ML require lots of data to process, and these GIS softwares lack the batch processing thing, and either they have and it is very difficult to have. So in that case, it will help you out. Now, which Python libraries are typically used? So one is the raster IO, which is used for geospatial geospatial raster data processing. So earlier there was only one library was available, and that was the GDAL, which is short form for Geospatial Data Abstraction Library. And after the Python came, then some of the so this Mapbox actually developed this raster IO, and it made it more cleaner in terms of opening and closing the file, as well as it made it more Pythonic. So it is very easy to work with. And most of the functionalities are similar in GDAL and raster IO. Second is GeoPandas. So Pandas you are already working in, I think. So it is the geospatial version of Pandas. Basically, it consists of these made up of these four libraries. One is Pandas, another is Shapely. Shapely is basically understand the shapes, the geometries that we have seen earlier. So it understands these kind of data. Then Fiona for file access and Matplotlib for giving you direct functionality to plot the data, the geospatial data directly on the matplot. Then NumPy, I think I can skip this one. So what is the typical flow chart to start with? So first you read the data, geospatial data that you have with you. It can be a GeoTIFF file. GeoTIFF file is georeferenced TIFF file. Another is HDF file format, which is a hierarchical data format, and another is NetCDF file. So these generally data are distributed in these three formats. So all these three formats can be read and can also be written by raster IO. So first you open the image or the data set that you have using raster IO. Then you read profile. Profile is nothing but the special information associated with the data. Then you read, which includes CRS and GeoTransform. You read raster bed and NumPy array. Once you get the NumPy array, you do whatever you want to do with this NumPy array. You can customize your algorithm. You can implement it whatever way you want. Then the output that you get at the end, you want to write in with the geospatial information that you have earlier in this profile. So it is very simple flow that you want to use. So now I'm going to see some live example. I'm going to show you some. So here are the references. Some of you might be interested. So you can go through these references if you want. Okay, so here I have one Python notebook with me. So just to give you introduction or some brief idea. So here I have downloaded one data set from the Bhunidhi portal that I've showed you. So you can go directly to the Bhunidhi Geo portal, make their your account, and you can download one sample data. So I have downloaded one sample data of AVIF sensor, which has 4 bands: band 2, band 3, band 4, and band 5, which are typically for green, red, NIR, and SWIR channel. So NIR means near infrared wavelength. It is basically wavelength of electromagnetic spectrum, and SWIR is short wave infrared, which is also a wavelength. So I have data with me in as a zip format. So it is stored on drive. So I'm connecting my drive directly. So you can mount your drive from drive.mount, and this is the path. We are using raster IO in this demonstration, but raster IO is by default not installed. So you have to install it using pip command. So basically this is the AVIF sensor. The AVIF is a sensor, and resource set 2 and 2A are satellites. So we have the AVIF's data, which comes in 4 band, and it is downloaded from Bhunidhi. This comes in a zip format, and if you want to see here, I have. Okay, so here you can see when you will download the data set from Bhunidhi, it will come in this format. Okay. So now let's say if we have data in zip, so first we have to unzip it. So for this, I'm using Python library called zip file, which will take the zip file and it will extract it. So I think it is very simple. So now the data is extracted over here. Yeah. So this is our data set. So here data comes in separate bands: band 2, band 3, band 4, and band 5. And this is the metadata associated with these bands. It will help you out to understand some of the geospatial information which are in this metadata, and it will help you understand the data. So first we have to read the band meta so that we can understand the data. So next is we are reading the metadata in band info dictionary. So here you can see some of the important parameters. Yeah. So it starts with product ID, satellite ID, Indian resource set satellite R2. So the satellite name is R2. Sensor is AVIFS. So AVIFS sensor basically consists of 4 subscene A, B, C, D. Okay, so it has the 4 camera in that. So we are working in the subscene number D. The generation RSC is NRSC, path and row. Why it is important, path and row? Because the area on which you want to work, it will typically come on a particular path and row of the satellite. So you have to know that on which path and row it is coming if you want to directly order from the NRSC based on the path and row information. So the date of pass is 5th June. So the uh, satellite was going in this took this image on 5th June 2025. So their total number of bands are 4. Band number 2345. Date of dump means the date on which this data was processed. This is one of the important thing, bits per pixel. So typically the data, the radiometric resolution that we were discussing on the earlier lecture is nothing but these are the number of bits which is used to represent the electromagnetic signal that we are receiving on the sensor. Okay. So if I increase my bits per pixel to let's say 16, which means I can differentiate more closely between two intensity of the electromagnetic energy I am getting at the sensor. So that is why it is important. Now, this is the input resolution along and cross. So this will tell you along means in the direction of the satellite. Across means uh, in the in the uh, 90-degree, I will say the horizontal direction. In case if the satellite is moving this side, then in the horizontal direction it will be called as a cross direction. So the original resolution was 66, but for developing the product, generating this product, we are resampling it to the 56 meter. So the image format is GeoTIFF. The total number of scan and pixels are 8135 and 8920. Map projection, which I said is very much important to you, is LCC, which is short form for Lambert conformal conical projection. And why LCC? Because it's a conical projection, which means we are using cone. So it is very suitable for mid latitude. India comes in the category of mid latitude. So that's why we are using LCC over here. Some ellipsoid datum, all these things. Then another important thing is product upper left latitude and longitude. So these are the common format we are using. We see actually this is called the GCS projection, geographic coordinate system, in which we typically give latitude longitude to some other person. But in case of LCC projection, these are the parameters which are in meters. Then now these are the scene center, latitude, longitude, and all these are information related to CRS. Okay, because it is a conical projection, you have to give standard parallel 1 and 2 because there are two directions in the conical which will be touching on our surface. So that's why we have standard parallel 1 and standard parallel 2. These are the projection parameters. Some other projection you may not see it. Now, at the time of capturing the scene by the satellite, at what position sun was, this kind of information is given here. So it is very important. Sometimes you want to remove the shadow from the image that you have captured. You want to remove the cloud shadow. You want to identify that thing. So you know the sun is there, satellite is here, and the position of the cloud. And based on the trigonometry, you can identify at what area the shadow is coming, and you want to remove that one. So in those kind of application, you can use this information. Apart from that, there are some sensor specific information because these are the electronics sensors. So they have some temperature after which they do not capture the readings. So these kind of information is important in case if you are correcting your correcting the energy that you are receiving at the sensor, which means you are converting the DN values to surface reflectance. So these information are important for that purpose. So all these information is available in metadata and you can identify which of the information is related to you. In my case, because this is a simple example, I will use the CRS and the geotransformation information. So CRS here is LCC with some standard parallels and geotransform is the upper left latitude longitude. 56 meter is the resolution in X direction and the Y directions. Now, if I have how to read this kind of data, these data which is coming in GeoTIFF using raster IO. So basically raster IO read all this information directly from the image that you have. If you have HDF data set, maybe some of you are working on that particular file format or the NetCDF format, you can directly give HDF and NetCDF file. So raster IO will tell you some of the information like what is the width, height, the CRS. It is the CRS in WKT, that is well-known text. Also, it can be seen here in the case by type string. So this is the transformation information. Here you can see. So 56 meter is the resolution. This is upper left X coordinate. This is Y coordinate. This is in Y direction. What is the resolution? And this is for shear. Basically, raster IO sees as a fine transformation matrix. So a fine transformation matrix means X, Y as well as some shear information. You can also get the bounding box of the image directly from here. So these are some of the information which can directly seen or directly can be interpreted from the raster IO. So these are this is basically transform parameters. I'm just giving you the example that is scale in X direction, rotation, translation in X direction, all these 6 parameters that we have discussed earlier in presentation also. Now, while processing for the satellite images, you may need to stack all these bands because the more information you will get, the more classification power your model will get. So that is why maybe it is required in your case that you need for a particular location what is the value of red band, green band, NIR band, and sphere band. This kind of information you want to have. So in that case, it is required to stack all the bands together. Okay, so X and Y axes will have the longitude and latitude, and in Z direction you will have the band information. So for stacking, we have raster IO. So raster IO basically take np.stack. So all the arrays, basically, let me give you some explanation of these code. So basically what you did here, that you have the band 2 path, band 3 path, 4 path, and 5 paths, because the folder originally have all these bands as an independent or a separate file kind of system. So basically you have given the path, you stacked it, you actually read all these information as numpy array, you stack basically based on np.stack, given all this list in this order, that first band will be band 2, then 3, then 4, and then 5. So this will be your stacked image basically. Now the profile thing, whatever I am generating over here is nothing but the profile. Okay, so I want to update it because earlier there was only one band, right? I have my CRS which is same, I have my geotransform information which is same, because I am doing nothing but only appending my bands, stacking my bands. So I am increasing my number of bands, but I am doing nothing with respect to the changing or updating spatial information, right? So in that case, you have to update the profile. So we have taken the band 2 profile as it is and only updated by only updated the number of bands. Earlier it was only one band, but now it has 4 bands. And now I have my numpy array, I have my profile in raster IO object. Now I want to write it in geotiff. So basically this is the path, the output path on which I want to use, and this is how we write it. So we have given it as a parameter the updated profile. Also we have given the stacked numpy array, and based on it will write it. So let me run it. And raster IO also have one function called show, raster IO.plot import show, which can read the geospatial information which is associated with this data set, and it will help you out plotting of the image with respect to the spatial information, like with respect to geotransform. So it will help you out that this image belongs to at what location. Okay. So this is LCC projection, but it is still hard to understand for us because we don't know that which projection system we are working on. Typically, as a standard for paper writing or for giving the references, we use geographic coordinate system. Okay, so we have to reproject from this projection system to another projection system. So next example is how to change the projection of one image from one projection system to another projection system. So here the LCC projection is projection system was the input projection, and WGS 1984, which actually it has one code EPSG 4326. EPSG is basically European Petroleum Survey Group, which uniquely identify or given some standard codes to every projection, because they otherwise there will be millions of projection. You can also develop your own projection for your which can give accurate CRS for your local area. Okay, so there is a need to standardize this thing. So EPSC did that, and it gave some of the numbers, 3-digit or 4-digit or 5-digit numbers to various projection systems. Okay, so here for changing the projection, we use raster.io.warp. Warping means we want to generate some surface, or we want to reproject, because reprojection is nothing but changing one surface or one data from one coordinate system to another coordinate system. That is why we are using here warp. So for warping purposes, we will use default transform, reproject, and resampling. So I will tell you that each one in detail. So we have stacked path. So this is the image that we just stacked in the previous cell. Now we have this image with us. We have to using the calculate default transform, we have to identify the corner coordinates of this image if by assuming that we have changed our projections. Correct? So for this we use the calculate default transform. It will take you the source CRS, which is LCC projection. It has taken directly from the image. This is the projection. It is our destination projection, basically target projection, in which we want to get our corner coordinates. This source width and height is nothing but the number of rows and columns, as well as we are giving the bounds with it. So it will give you the destination transform. Destination transform is the values in the coordinates in the corners in EPSG 4326. And it may happen because of the change in the projection, the pixel size in X direction and Y direction may change. So that is why we are also getting width and height, updated width and height. Okay. Once we have got all these information, we want to update the profile, because for writing a raster IO object, you need two things. One is profile and another is numpy array. So we want to update the profile that we have earlier in our example. So we copied this profile, we updated those information where we have made changes. For example, we changed our coordinate system, which is now EPSG 4326. Transform information we have changed. So that information is given here. Width and height is given here. Here I have changed no data value, because in earlier image, the no data was not given. But here I explicitly mention it. Okay, whatever pixel has the value 0, please do not consider as a valid pixels. Okay, that is also one of the capabilities of GIS software, which is not typically given in computer vision libraries, where you have to do something. Let's say if you want to calculate the statistics, finding the statistics from using raster IO on geospatial data is easy because it understands no data values. But in case of the common computer vision libraries, you have to mention some of the code, or some explicitly you want to mention, or you have to filter it for generating the statistics. Okay. So now we have the updated profile with us. We have the stacked image as numpy array. We want to write it, but we have already given the parameters of. We have just the updated parameters. We have not explicitly told to the GIS software to do the projection. So for this thing, we use the reproject here. So raster IO object has this function called reprojection, which you can directly use it. Here you have given that this is the source. For each band you want to do the projection. So therefore we have one for loop for from 1 to number of band. Here you will see that we are starting from 1, because in GIS software band number always start from 1. In Python you start indexes from 0, but here you have to take care. So source, destination, what is the source transformation? What is the source CRS? destination transformation that we computed from earlier in this line, then destination CRS, then resampling method. By which method you want to do the resampling? By default, in most of the GIS software, it is nearest neighbor. So whatever pixels, what is the when you do the warping, okay, when you do the reprojection, whatever pixel in the original image is near to the updated pixel, the same value is copied to that pixel. So this is the nearest neighbor. But there are several other resampling method also, like bilinear, linear, all this. In fact, cubic is also available, but all those are means time consuming. It may take some time to generate resampled image. So if I run it, one more thing here I want to tell you that I have a stacked image of how many bands. Just I want to ask you one question: that how many bands were there in a stacked image? Anyone? 4. But here I am display only 3 images. Oh, sorry, 3 band image, because RGB, when I visualize it in RGB, I can only choose 3 bands. Okay. So there is a term called false color composite, where we give red band or red color to that particular band, which give us more information. Okay. So in case of vegetation, NIR has high variability in terms of data, and therefore we give red color to NIR band. Similarly, we give green color to red wavelength, basically red band channel, and blue color is given to green band. And that is why we see here this image, the vegetation you can see here is in red color. Of course, you can increase the tone and all these things, because that comes in the image processing. Because of time limitation, I have not done that. But here you can see that these all red part is nothing but the vegetation. These are the cloud part. As you see, cloud typically appears white in an image, so as snow. This is water. Here you will see some different tone of water here, which is because of the pollution that we make. Some of the sediments of the river carried by some of the sediments that are carried by the rivers are taken to the ocean, and because of which you can find some different tone of water. So all these information you can directly see from the satellite image, and it will help you to classify or you understand what is the natural phenomena that is happening. Okay, so one more example, since it is a FCC image and we want to see the vegetation, therefore our eyes are more sensitive toward the red color. That is why we gave it as a red color here. For some other application, you may find some different channel combination or the band combination for generation of FCC. So remote sensing, in remote sensing, we in previous lecture, we saw one index called NDVI. Now we want to compute that particular index. So how do that? It's just an example of band statistics. You can have n number of indexes in remote sensing. You can do any linear combination of the bands you can calculate based on once you know how to do that. So C is as an example of how you want to do band statistics, means and first band multiply by some constant plus some another band multiply by some constant, some kind of this kind of calculation you can directly made here. So yeah. One more thing here I want to explain, that let's see that I have this image, but I don't know that I can geographically, or maybe I can from inspection I can find out that this is the Bay of Khambat. Okay, this is the Gujarat part, Gujarat, and this is the coastal region. But how can actually we find out using vector data? Typically, vector data tells us the administrative boundary. So I want to also see that if I overlay my vector boundary on this image, how will it look like? Okay. So with these two objectives, this cell is, I have written this cell. So here you can find I have taken the administrative boundary of Gujarat from Google Earth Engine. So if you are using this Python notebook directly, maybe after this session on your local system, you have to change here you have to give your own Earth Engine project name. Okay. So that is the one thing that I want to tell you. But in case if you have this shape file or this geometry with you offline, then you can directly upload it on the Google Drive and directly use it. So basically, this is the geometry, just to give you some idea. Okay, meanwhile, I can tell you that how to calculate NDVI. So NDVI is basically NIR plus red divided by NIR minus red. So where NIR and red variable here are surface reflectance, but we have not computed surface reflectance. We are using the DN value, digital number that we are getting from the images directly. And to avoid the denominator dividing by zero error, we wherever denominator is zero, uh, I am giving NDVI value as zero directly. So once you calculate the NDVI, obviously NDVI will be only one channel. So what we have to change? Anyone? We have profile of our earlier image, that is the stacked image. Okay. So after calculating NDVI and to write NDVI in GOT format, we have to change our profile. Can anyone tell me that what changes we have to make in profile? First, what profile consists? Profile has what kind of information? Band, yes. First, we have to change the band. Second thing is that data type, because earlier the DN values were unsigned integer 16 in that format, but NDVI will be a value between 0 to 1 kind of, and it can be like 0.4326. So we have to change our data type. So here what I have taken is the whatever stacked image profile I had, I copied it. I have changed only those information which where I have made my changes. Okay. So this is the same thing. You have some NDVI path, output path. You want to write it directly, you can write over here. And this is to visualize. So this is the boundary that we got from Google Earth Engine here, and we overlay on the NDVI profile. So it can you exactly tell you, because it is just a Gujarat administrative boundary. You may get, in fact, you can get the administrative boundary of taluka level also, village level also, and it can directly give you that at what location um, your NDVI is. This kind of information you can directly interpret by seeing it. Okay. Now the same thing I'm doing for Surat, because in this Gujarat I can see that my image or the area of interest is, let's say, this particular region where you can see the high NDVI value, which means there is more vegetation in month of June. So, okay, but for this I have to change my administrative boundary or my geometry from Gujarat to Surat. Correct. So here this is the FAO boundaries are available, and here I selected Surat from Google Earth Engine, and all the NDVI image I have already with my this cell. So I just overlaid Surat over here. And one more thing I did is that since my area of interest or ROI is just Surat district, so I don't want to keep the data set outside the Surat boundary. So that operation is called clipping of raster image based on some geometry. So that is also helpful in case if you have, because typically satellite data comes in bulk. I mean, they capture the lots of information in a spatial domain, and you want to only consider your AOI. Okay, so in that case, you want to do the clipping thing. So that particular clipping is done over here. So for doing clipping, we use mask function. So here the geometry is red in as a feature collection, because yeah, geometry is red over here. We gave SRC. SRC is nothing but the raster IO object. Geometry is the geometry which consists of the coordinates of the boundaries with us, and we gave it where we want to crop it. So this operation is given, it will give you cropped image, because once we do the cropping, obviously the upper left latitude, longitude and all this information will be changed. There will be no effect on the pixel size in the pixel resolution, but definitely there will be changes in upper left latitude, longitude information. So therefore, it will give you the cropped image as well as the geotransform information of that cropped image. And the metadata, the same thing, that we have the metadata earlier and we only changed some of the information here. So this will help you to find out the clip time behavior. Okay, in some of the application, it may also happen that you require, you want to display this particular image on map so that you can directly link based on the human addresses, like generally what we do to get to a particular location. We have some sector 43, some address near this particular school, something like that, but which is not possible here in this case. So you want to overlay it on some map to understand what is to understand the natural phenomena that is happening on that particular location. So in that case, we are using Folium map. And if I run it, so it has Folium has a raster layer which can directly help you out. Takes the NumPy array as an image and it overlay on the map. So this is the area on which we are working, and if we see it on this map, okay, there may be some issue with the map, but in the starting you must have seen some map was coming there, but I don't know why it is not loading over here. Yeah, it is coming here. So here you can easily identify that which area this particular pixel belongs to which area. And this is the Tapi River, which can clearly identify you from this satellite image. So these kind of geoprocessing will help you out to understand more the satellite data. It will help you to get more information that will definitely will help you out in developing your AI/ML model. And sometimes it so happen that when you work on the satellite data, you want to also explain. Let's say you are trying to develop some understanding of the local phenomena, then you have to give the results in the paper with respect to the coordinates, because some these coordinates not only tells us the location but also geography and the climatology also, which may be help to understand that particular phenomena. So that is why while working with the satellite images, you have to just go through these kind of information also, not just discard the spatial information and work with the images, but sometimes you have to link coordinates also with respect to the result you are getting by AI/ML model. Okay, so this is from my side. I hope that it will help you out to understand the satellite data more. With this intention, I'm closing this session. Thank you. So if you have any question, you can ask.